Thank you so much for the introduction, and thank you to everyone for being here. It's a real honor to address you all. That's a great start, because the slideshow doesn't work. Well, I don't know what's on the screen. Can someone assist with the slideshow, please? Terrific. That's not the slideshow. Where's the PowerPoint gone? No, it was on the OneDrive. Where's the OneDrive gone?
We're almost there.
Okay.
Okay. There we are.
No.
Should be perfect now. Okay, yes. My apologies. That's perfect, isn't it? Great start. Okay, so this is a picture. I asked the machine to visualize what my talk should be, and this is the answer, apparently. ChatGPT is a wonderful thing. I don't know if it's very accurate, but it looks kind of cool. There's circles, and there's space, and there's time, and that means something. Okay, so, you wouldn't think it talking to us, but we're actually very humble people, physicists. And, we are aware that we have, or at least people perceive that we have, some shortcomings. And I just wanted to start the talk by addressing a couple of those. So a personal story. When I first joined Swansea, I did our very excellent teacher training program. And the first session of the teacher training program was, what does great teaching look like? And slide one was a picture of a room of photogenic young things, much like yourselves, staring intently at the lecturer. And that's what good teaching at Swansea looks like. And of course, the slide two is what does bad teaching look like? And this is what they showed. They showed a picture of a white guy who looks a bit like me with equations and blackboards. Right, I thought, welcome to Swansea. The next slide, just to emphasize the point, was Homer Simpson and a blackboard of equations. Okay, and I found it funny. I was also a little bit wrinkled by it, because it's right and it's wrong, okay? So this view of physics, it is, there's some truth to it. A bunch of equations, it's very austere, it's not very welcoming, it's, it seems like an alien thing. But it's also wrong, of course, because this is the language that we use. There can be great beauty and power in equations. And of course, it takes some effort to get there, a bit like reading sheet music. But that's what we do. So both of these characters will play a role in today's talk, and we'll come back to them. Okay, that's Richard Feynman. So the first thing I want to talk about is the problem with physics. We need to address that. But then we'll go on from that, and I'll try and bring a way of thinking. I'm not going to really explain the details of my research, but I am going to explain my outlook on things and the way I motivate my problems by talking about the principles that modern theoretical physics uses. Then we'll get a bit more crunchy, a bit more specific. I'll tell you what string theory is, what dualities are. I mentioned them. I'll tell you about holography, integrability, lots of stuff, depending on time. Okay. So the problem with physics, we have a perception problem, I told you about it. We also have a legal problem. And the legal problem is when you first sort of encounter physics at secondary school or A-level or even first year undergraduate, you get bombarded with this kind of stuff. A myriad of laws. Physics is full of laws, right? And, to apply them, you want to know how will this electron respond to this magnetic field? You need to do a thing, or maybe it's that one, or is it that one? I can't remember. And you need to know all of these laws. And they're all true. They're all amazing. They all predict the world. But it's not very edifying. Firstly, it's pretty tedious to learn all of these laws. They all have names. I can't remember what the names of most of them are. They're all very accurate at the precise phenomenon that they're describing. So they have specific but limited validity. They kind of seem a bit arbitrary. Where did they come from? What relation do they have with each other? They all seem a bit different, but maybe they're not. That's quite hard to understand. And they all work great until you try and push them a little bit too far, and then they don't. So what do? Do you have to cook up a new law? And do we keep doing this forever and ever, just cook up new laws? That's a bit frustrating. So, this is kind of what physics is like, either in, 1902 or in first year physics. And I guess what I wanted to say is that's not what we actually do. Okay, this isn't how physics works for us in the theory group, at least. So we're not going to worry about laws, minutiae of laws. We're going to talk about principles. Okay, so I want to go from this landscape of laws to just 5 principles. Now, these aren't written in a book, so these are my principles, and other people might have other principles. That's free choice. So the first principle is that nature has a cost function. Okay, I think a cost function is something probably fairly universally known across the Faculty of Science and Engineering, certainly across businesses, but it's also true in physics. So I'm going to explain what this means. The second key law is the law or principle of symmetry. Symmetry underlines everything we do. The third one, and this is really the most important thing that every person on the planet should know, is the world is quantum. And that underpins everything. So, cost principle, symmetry, and quantum. Now we're getting a bit more abstract. The world is geometric. And I guess another way of saying what this principle is this is the principle that mathematics works for physics. And we'll see more about that. And the fifth principle is one of unification. The idea that as we learn more, things get simpler. So if we can solve all of these things together, we're on the right track. So what we'll do is we'll go through these principles a little bit. The first principle, nature has a cost function. But here's 2 apparently quite different things. The first thing is a rugby ball being kicked over the posts. The second thing is some light hitting a glass block and diffracting and coming out the other side. Okay, and both of these things, we could go back to the first slide and pick the right law. Right, we could have used Snell's law, or we could have used Suvat equations, or I don't know what. Very good. The point is, both these features, distinct as they are, they follow from the same thing, which is they minimize a cost. And the cost here is called the action. And we use the symbol S, I don't really know the historical reason, for action. So this is a cost associated to this process. We look at all possible paths that the rugby ball could follow, and we measure the cost of each of those paths, and it turns out the one that nature actually follows is the one that costs the least. Very good. And being a bit more crunchy about it, the action principle is something like the kinetic energy minus the potential energy. Okay? So you can write down an action principle for this and for this. Now, if I say, well, here's an action, here's a cost function, what's its minimum? You need to know a bit of mathematics. Unfortunately, this is a solved problem. The titans of classical mathematics, this is the northwest face of the Eiffel Tower. It has Legendre on it, it has Legrand, has a whole bunch of people on it that contributed to the understanding of how to minimize cost functions. It's a nice bit of mathematics, classical mathematics. So you go from your cost function, and out of that you find some differential equations. And those are the laws that we had at the beginning. So they're derived from this principle. Okay? So that's great. The job's not quite done, because here we are. I've managed to obtain Newton's law, F equals ma, you all learned that one, from a cost function. But we still have some differential equations to solve, and that can be a little bit hard. And I'll come back to that. But also we have a bit of choice in what we write down for this cost function in the first place. So it's not fully solved here. Okay. The second principle is symmetry. I think we all have an idea of what symmetry is, and probably we all apply it in our research in various guises. Here's a triangle. It has a symmetry, it has reflections, it has rotations. And if you know a little bit of mathematics, you know that they compose into a group, and that's what this little table, I'm not going to explain the details, indicates. And that kind of basic understanding of symmetry is what we do in theoretical physics. But more precisely, what we mean by a symmetry is a transformation which doesn't change the cost. Okay, so if I think of the cost function of, here's some configuration of stuff, little arrows pointing up or down, and I measure the cost. Suppose now I swap every downward blue arrow with an upward orange arrow, which is what I've done on the other side, and the cost is unchanged. That's a symmetry. And if that happens for every possible configuration. So symmetry costs nothing. It preserves the cost. But, and this is a crucial bit, it buys us an awful lot. So this is a picture of Emmy Noether. I think in all of our undergraduate education, she is probably the most referenced person in our second and third year and fourth year modules. She's very influential in the way we address modern theoretical physics, because it exposed the way that symmetry is intimately related to conserved charges, conserved quantities. So you all know that total energy of a system is conserved. Total momentum of a system is conserved. Those are kind of basic things. The reason they're conserved is there's a symmetry. In one case, it's the symmetry of time translations. Physics tomorrow looks the same as physics today. And in the other, it's spatial translations. Physics over there is the same as physics over here. And that's great, because when we have a conserved energy or a conserved momentum, we can try and solve some differential equations more easily. And I call them conserved charges, because sometimes the conserved quantity really is what we think of as a charge, the charge of an electron, an electric charge. And that relates to a different sort of symmetry, some internal symmetry. Although, sidebar, you know, I love symmetries. Turns out nature also really likes breaking symmetries. And I tried to make this appealing across the faculty, and that's my limit of my knowledge, which is that snail shells spiral in one direction preferentially, rather than equally, or at least these snails do. And yeah, this amino acid occurs in its left-handed chirality in preference in nature, in proteins. The world is built out of matter and not antimatter. That's a really important asymmetry that we're very keen on in Swansea physics, and we don't really understand why. So symmetry is very important, and for my talk, symmetry will always be there, but in nature it's quite often broken. Okay. So, cost function, symmetries. Now, the world is quantum. What does this mean? If we look at small scales, we'll find that systems can't occur in any possible energy. They can only occur at very discrete, specific energy levels. And that's the word quanta. It refers to these discrete levels. So that's one manifestation of the world is quantum. But the other one is that the world is intrinsically probabilistic. Now, I don't mean probabilistic like the rugby ball might or might not go over the posts if the kicker's rubbish or good. What I mean is that any measurement you do will always have an element of probability in its outcome. And that's what this formula here symbolizes. It actually means something, but I won't go into the details. So now back to the cost function. So I told you that the path the rugby ball followed was the one that cost the least. I lied. Actually, in the quantum world, we have to consider every possible trajectory that could have been followed by a particle, and we give them all a cost. And we kind of average over all of these costs, or we sum over all of these costs. It turns out that the classical trajectory that you know is the one that makes the biggest contribution, but all possible configurations are taken into account of. So nature not only is frugal, it's also an accountant. It follows every single trajectory. Okay. Principle 4. The world is geometric, nature is geometric. And what do I mean by that? So I think you've probably all seen a rubber sheet analogy of how does general relativity work. Space-time is some fabric. You put a piece of matter in it, and it back reacts and bends the space-time, and that's how we understand gravity. That's actually geometry. So what we've got here, this is a very famous equation. The details don't really matter too much here. This side of the equation tells you about the curvature of an object. That's a very geometric thing. And this side of the equation tells you about the stuff. So you've got an equation there which is curvature equals stuff. So gravity is definitely a geometric concept. But also, so too are fundamental particles. Now this is a bit more abstract in terms of mathematics, but if you want to understand your force carriers, your photons, your gluons, or your charged particles, your electrons or your quarks, these are understood in terms of mathematics of something called fiber bundles. I don't think I can give a course on fiber bundles, but here are some pictures. I guess this one's quite a nice one. This is a Mobius strip, right? So a Mobius strip is a circle, and at each point on your circle, you've got a little interval, a line, and as you come back round the circle, those lines are glued back with a twist. Okay? And that is what a Mobius strip is compared to just a normal bracelet. And that's an example of a fiber bundle. This is a three-dimensional sphere drawn in a funny way. That's also a fiber bundle. But the point is, all of our fundamental particles are accessible with the mathematics that describes these sorts of things. Okay. All right, now this is a picture of everything, right? Everything we know. And it's a slide about unity. So if we're reading this, we can read this from left to right in a variety of ways. So we can read it in terms of sophistication, that's one way. We can read it in terms of time of discovery, or we can read it in terms of energy scale, or we can read it in terms of amount of maths you need to know. So what have we got here? We start with electricity and magnetism, that's what we begin with, and then there was light, and then we add in some special relativity, and we get to, I guess we're talking what, we're in 1906 now. We've got differential formulation of electromagnetism, classical electromagnetism. So electricity was there, magnetism were there, but now they're one thing. And then we add quantum mechanics to that mix. So we need Dirac at this point, and we have this new theory of quantum electromagnetism. And that's what this diagram indicates. Tells you actually about how light scatters off light, which is something that doesn't happen classically. Okay, so two different things merged with special relativity, merged with quantum, gives this new thing, quantum electrodynamics. You know, but there's other forces in the game. So Curie discovered that we had radiation. So there's a weak nuclear force, beta decay. But that enters into the mix as well. It turns out we can combine the radiation, the weak forces, with the electrodynamics into a new package. Sometimes it's called electroweak unification. And this picture here, this picture represents the Higgs mechanism. You've heard of the Higgs particle, right? That's really to do with this part of the unification. There's other forces in the game. There's the strong nuclear forces that are inside the nucleus of an atom, and that's what this red, green, and blue indicates. That's the quark model. It's not really clear quite how they should unify with the other forces, but there's pretty compelling evidence that suggests at some energy scale, those things are going to be different features of just one unified package. So that's the first question mark. At the bottom of the slide, though, there's a seemingly different thrust of work here. This is an apple tree. It means gravity. Yeah, creative as well. Now, if we combine gravity, with special relativity, you need a new theory, actually. You need Einstein's general relativity. And that's what this picture indicates, and this is, an inspiraling merger of some black holes. The kind of thing that actually you can now observe in the real world and win a Nobel Prize for. So that's already some unification going on. But I guess one would hope eventually on the end of this very long arrow that this stuff is not really so different from the particle physics-y stuff, and that these things will all merge together. So I suppose this arrow is where I want to go to eventually. So those are the 5 principles, but there are some gaps. And, gaps are great, actually. Like, for a theoretical physicist, if there were no gaps, I wouldn't have a job, so gaps are really good. So how do we make gravity a quantum force? How do we put it on the same footing as other forces? Can we actually bring a bit more mathematical robustness into the definitions of some of these things? There's a little bit of hand-waviness that I didn't really explain, but how can we make them a bit more robust? And what are these big question marks on the right-hand side? That's my problems. Now, we're a mixed bunch in the theory group, and we all have slightly different takes on what the big problems are. So you get to choose your own big problem. That's something really nice about academia, but these are mine. Okay. Right, so now I'm going to get a bit more meaty and talk about stuff closer to my research. So the first thing I want to talk about is string theory. Now, I don't want to try and sell to you string theory is the answer to everything and we should all go home. I think the situation is far more nuanced than that. But what it is a very rich paradigm that seems to be leading us in some very exciting areas in mathematical physics. So, a principle I never told you was that everything should be made of points. I never said that. Don't know. Doesn't need to be true. So let's flex that. Let's just assume, let's see what happens if we just say, maybe our fundamental objects aren't little points. Why not? So what's the simplest thing that isn't a point? It's a thing that's just got a length. So the simplest possible idea here is we consider a one-dimensional object. Here's a one-dimensional object sweeping a path through time. So if it's got a length and it moves through time, it has 2 dimensions on that surface. Yeah? Whereas a point particle would sweep a line through time. So now, there we are, that's my idea. We need a cost principle. That was principle number 1. We need a cost function for this. And let's pick the simplest possible cost function we can. So a geodesic minimizes its length. That's what a geodesic is. That's the cost function for a geodesic. So let's try the same thing here. Let's make the area of this sheet be the cost function. This is exactly the same as if we were doing soap bubbles. So if I had some buckets of soapy water and a thing, and I could do a nice thing with soap bubbles to illustrate it, it would be the same physics at this point. If you want some formulas, here's a technical formula for the action of a string. So a really simple idea. So we've looked at the cost principle. Now we have to impose the quantum principle. So we take this string and we do first stroke second year quantum mechanics on it. And we just see what happens. So what are the allowed energies of this string? And it turns out one of the ways in which this string can vibrate at a quantum level is, in jargon, a massless spin 2 particle, or a graviton. To de-jargonize that, what I mean is the excitations of the string contain the quantum particle associated to gravity. So this string wasn't an input, this is an output, knows about gravity. In fact, more than that, if we look at the symmetries of this string, the symmetry principle, and combine it with the quantum principle, we find actually general relativity itself emerges from this object. So again, general relativity is an output, not an input. And then the unification principle turns out that this string also contains other things as well. I'll come back to them in a minute. So it sits very nicely in terms of all these principles. And it has some surprises. Here are two big surprises. Some people say string theory makes no predictions, and of course that's totally untrue. It makes a very bold and probably wrong prediction about our universe. It says the universe must have additional dimensions to what we see. So it must have multiple extra dimensions. How can that possibly be true? Well, actually, to what we see. That's talking about our human scale probes, our current state-of-the-art microscopes. So it just means that we have to look beyond the energy frontier. These extra dimensions, presumably, because we haven't detected them, must be too small to be detected. Now, to describe what they look like brings you into a very exciting realm of algebraic geometry and Calabi-Yau manifolds. I'm not going to explain them, but back to Homer Simpson, you can basically think of all these extra dimensions as donuts. True. So we're going to come back to these donut dimensions in a minute. The second big surprise about string theory is it's not actually a theory of strings. Right? That's what I put in just now. What comes out is, in fact, it contains not just strings, but also hyperplanes of energy called d-branes. So that's what I've drawn here. So here are the strings I put in, but then I also found out we had these big planes of energy onto which strings can end. Now here's a neat feature. Look at this purple string. It's ending on one of these branes, and the endpoints of these strings are points. So I tried to get rid of the points, but they came back. I couldn't get rid of them. They're there. The point particles have re-emerged in the guise of the endpoints of the strings. So actually, string theory contained the quantum field theories as an output. That's pretty cool, right? General relativity came as an output, so did quantum field theory. Okay. I'm going to move on now and talk about some core concepts of duality. This is Janus, the Roman god, two-headed god of duality and other stuff. They all had multiple roles. They must have had some cost pressures. Duality is the equivalence between superficially very different theories. Okay, so I have one theory over there, it looks like apples, one theory over there, it looks like oranges, turns out they're the same. So that's one idea of duality. The other idea of duality could be I've got a theory and I'm applying it in very different regimes, and it turns out that's also the same. This is quite a powerful concept in theoretical physics. It's often very subtle as well. It's not obvious, but it is quite pervasive. So on the slide, I illustrate two examples. The one here, this is some lattice of spins. That's like some, condensed matter type physics. And this has a duality, which tells you if you want to know about this crystalline lattice or whatever it is at a high temperature, it's actually the same as at a low temperature. So you have a temperature inversion duality. That's kind of useful. The other one, and this is kind of important for Swansea, is electromagnetic duality. If you take the laws of electromagnetism and switch what you mean by electric field and B field, magnetic field, so switch E and B over, the laws of electromagnetism are preserved. That's not quite true at the quantum level, but there are systems where this is true, at the quantum level. In fact, they were developed by David Olive, who founded the theory group here at Swansea. So this is called S-duality, very rich mathematical idea. I love duality. There are two motivations I have for duality. The first one, I love it, it's fascinating. I'm fascinated by it, and that for me is enough to study it. I think it warrants deep mathematical exploration, and having a duality probably defines physics for you. So I think that's one key motivation, a kind of mathematician's motivation. A physicist's motivation is that duality is useful and practical and we can calculate things. So you can take theory A and ask a problem in theory A that's really hard. Maybe it's a strongly interacting theory. Maybe we're at low temperature. Maybe it's non-local. Maybe the degrees of freedom are hard to pin down. But maybe, if you have a duality in theory B, it's all very easy. So you can make this hard question very easy in a different language. So the most crucial thing about this slide, of course, is the equal sign, which is a Welsh export. Very important Welsh export. Okay. So in string theory, we have duality. And the duality that I care most about in string theory is called T-duality. And for me, it's signature of string theory. It exists because strings are not point particles. So what do I mean by this? Here's one of my donut-shaped dimensions. It's a dimension, it's small, it's got radius r. Now, because a string is a point particle, it isn't a point particle, it can do an extra thing. It can wind around this cylinder, wind around a circle of the donut. That's something point particles just don't do. And because of that, it turns out from the point of view of strings, this small circle, this small space, is exactly the same as a very big space. This is just a weird thing, right? Small and big are the same thing for string theory. For me, that's the defining feature of strings. And I try and understand this very carefully. So this is now a bit more onto my research. And this is the work that I was doing in Brussels before I arrived here. And I was interested in understanding much more about what these dualities in string theory are and how can they be flexed. So instead of considering circular spaces where we've got duality, can we consider other sorts of spaces? Here's a sphere, or we could be looking at other sorts of stuff. So this is an idea called non-abelian duality that's had some mileage. And then parallel to this has been a thrust of work. You use the words exceptional something or another in the blurb. Right, okay, that's what this is all about. So strings are not point particles. They see geometry differently. Yet most of the time, we use the same language that we use to describe geometry for point particles. And that doesn't feel right. We should use some language of geometry that's better adapted to the fact that strings are strings. Unfortunately, there is a language here. It's called generalized geometry. It was pioneered by a great British mathematician, Nigel Hitchin, and here's some lovely maths behind it. A lot of my work has been understanding how to employ the mathematics of generalized geometry to understand how the strings see space and time. Okay. Right, and now this is the slide that explains why I'm here in Swansea. There's one other duality that I didn't talk about yet. I hinted at it, but I didn't tell you about it. And this is probably the most shocking revelation for theoretical physicists in the past, 40 years. Quantum field theories, the theories that describe particle interactions, can actually be equivalent to gravity. So we can repackage certain particle theories as gravity theories. Now, there's quite a lot of caveats and elaborations to specify exactly what I mean by that. But this is a duality of the highest caliber, because we've got very difficult quantum field theory, very easy gravity theory. So we can translate very hard problems in quantum field theory to very easy problems in gravity. And so, having worked on this idea of these dualities, these non-abelian dualities, Carlos and I set to work to try and understand how could they be applied within this idea of holography. And that sort of opened up a whole new pathway of developments and was kind of the cornerstone of my URF, my Royal Society Fellowship, was harnessing some of these ideas. And that's, how I ended up here in Swansea. Of course, my family is originally from Swansea. That also helped. We go back to a very famous family of hoteliers on the docks. You can ask me about that later. Right, now, a couple of technical slides for the experts. My more recent work has been on an idea called integrability. So circling back to Noether, Emmy Noether, right at the beginning, said symmetries were really good. They gave us conserved charges. I'm interested in some systems that have so many symmetries that we can actually exactly solve all of our differential equations without ever having to integrate anything. And if you're rubbish at doing integrals, like everyone on the planet, this is amazing, because you never have to. Okay? There we are. So that's a picture of phase space being foliated by conserved charges. So if you have one of these systems, this integrable system, you have enormous power to make predictions. You can transcend any other sorts of tools you might have. And what we've been doing is, or I, have been looking at this interface between the string dualities I mentioned earlier and integrable models. And at first they seem like very different things. Actually, there's a very close affinity between them. If you like, the duality is a very rich symmetry. So we've done lots of work here. Here's a cost function at the bottom that describes one of these integrable models that I work on. And this is a picture. This is three cliffs. Underneath three cliffs is an integrable version of three cliffs. That's encoding a very famous equation, the Yang-Baxter equation. And then we've deformed three cliffs, and then we've taken a mirror image of it, so we've dualized it. So this is the poster for the workshop we held this summer. I hosted here on the Bay campus on integrability, duality, and deformations. And that's what that all means. Okay. Right, in the last 5 minutes, I want to talk about psychology and quantum cognitive dissonance. Which doesn't exist in the psychology literature, though it should. But it's this. As a theorist, we are always suffering from cognitive dissonance. And the reason is this. Suppose we want to know the energy of some quantum system. Normally, that's quite a hard problem. So what we do is we say, okay, I want to know the energy E. I know what it is classically, because I can minimize my cost function. I can do that. And then I'm going to say it gets a little bit of quantumness, and then a bit more quantumness, and then a bit more quantumness. And if I keep working really, really, really hard, I can refine my estimate to what the energy is. That's called perturbation theory. And here's the dissonance. Perturbation theory is amazing. It's brilliant. We love it. We keep doing it because it's so good. It can lead to predictions that are accurate to 10 significant figures. And I think that's, as good as science in any domain will ever be. So, wow, can't get enough of it. At the same time, each and every one of us knows that it's fundamentally wrong. This equals sign here, Robert Record would be turning in his grave. It's not equals. The thing on the right-hand side is infinite. How can that possibly make any sense at all? The energy, I know what the energy is. I've measured it in the lab. It's 2.3. It's not infinite. Right? So fundamentally, this idea doesn't work. But yet it does. That's dissonance. But luckily, I have a therapy for this, which is resurgence. And this is sort of my hobby. My main research is the stuff I explained, but this is my hobby research. Which is this breakdown of perturbation theory actually encodes a lot of very nice, important physics And here we're harnessing very dark maths. I don't understand the maths, and I don't think the maths is understood by the mathematicians either, if I'm honest. Resurgent functions by Ekal. So the problem is, okay, I want to say that this chaotic, terrible series that's divergent, we can make sense of it. But to make sense of it, I'm going to need to calculate about the first 40 orders of this perturbation theory. I've only shown 3 on the board. I need 40 orders. And you just can't do that with conventional tools. But you can when you have integrability. Because I told you in integrability, you didn't need to solve any equations. So that's what I'm doing, is I'm testing this idea of resurgence using these integrable models that came from string dualities. And, you know, just to show you the kind of formulas and stuff you might expect to see in one of my papers, this is work with Lucas Scheppers, who finished his PhD 2 years ago, really demonstrating this conjecture of resurgence is precisely true. So, you know, this is analytic stuff, and this is several weeks of numerical work on a machine. And it all matched. It was brilliant. Okay. So, there we are. That brings me to the end. Some key messages. So, as we've seen, modern physics, we've moved beyond the rigid framework of laws. We've gone to principles. And we've seen that these principles, they're simple, but they can be applied across a range of phenomena. At the heart of it is a kind of economy, an economy principle, the cost function that governs physical systems. But you have to couple that with quantum mechanics. But to go further, you need to include some extra ingredients. We saw that geometry was one of them, symmetry was one of them, and unification or unity was one of them. So when you combine those with the cost function, with the symmetries, and the quantum, you're heading in the right direction. And string theory was an example of applying these principles that seemed to open some very rich mathematical physics, from branes to holography, duality being a kind of key feature. I guess, though, you know, it's fair to say that the big question marks I showed earlier, they are still, you know, distant targets. They're on the horizon. They are waiting for new insights. But my own take on it is, whatever the way we get there is, there's going to be a real symbiosis of mathematics, probably mathematics we haven't yet found, and physics. And that's probably where we've got to go. Okay, and I'll stop there.
Daniel, more of the question is trying to see how you see it. So you are working on physics, but as you are saying, the marriage with mathematics is where is this going? Right? I mean, this is asking for an opinion. I'm not asking you to make the future.
So, you know, there's a funny thing, right? There's a spectrum. There's a spectrum of theoretical physicists. So, you know, I look like a mathematician to some of my colleagues in the theory group, but the mathematicians over there look at me like some primitive Luddite. So, you know, this is a kind of a loaded question, right? But my view is probably the ideas that seem like abstract maths right now will become in due course, textbook and canonicalized and standardized. Things like group theory, probably physicists, when they first heard group theory, wanted to run a mile, okay, in the same way I want to run a mile when I hear about sheath cohomology, okay. But I think, you know, we will evolve as a discipline to be more embracing of what we think of as sophisticated maths. I mean, it's maths that was written 30, 40 years ago, right? But we think of as sophisticated. So yeah, my view is at some point we're going to have to become better at mathematics. That's what I think.
So, can I also ask a question / comment? So one of the things, and it's a follow-up to that also. So one of the things that we've seen in some areas of physics is that new mathematics gets discovered by looking at physical systems. What is your view on it in terms of how what you study might further actually mathematics? Yeah,
well, I can give a very precise example. I told you that we needed to use some new geometry, right, to describe how do strings see space and time. And the framework of that geometry was this Hitchin's generalized geometry set up by Hitchin. The thing they didn't have in that was the idea of curvature. It wasn't really a thing the mathematicians needed for the questions they were asking. We need it in physics because we want to do gravity. We need curvature. So there's a concrete example of something that was invented by physicists, curvature in generalized geometry, in the span of my research. So I do think that we will be generating ideas as well. Yeah.
Where do you see the interplay with experimental physics?
Well, I do, but I live on the very, very far right-hand side of that slide of unity, so I'm quite a long way away from that. Now, that said, you know, rich ideas about mathematics in quantum systems, be it topology and so on, do enter if you're talking about condensed matter systems and so on. So there are areas where rich mathematical physics can make direct application. But I'm not here saying I'm going to be calculating a next to next to next leading order process for a particle collider, because that's just not what my research is. I'm very glad someone's doing it, it's just not what I do. I'm looking at mathematical physics. So, yes, you're not going to get string theory in an experiment next year. No, you're just not going to get string theory in an experiment. I mean, that's just true.
Any final questions? I guess I'm just reflecting upon the first slide, which you said you used ChatGPT to generate.
Yes.
I wonder, given all the complexity of the math that can be employed, the extent to which AI offers challenges or opportunities for the types of research you're conducting.
Yeah, it's an amazing thing. I hadn't used it until a few months ago, and it's slightly terrifyingly good. It's like a kind of, at the moment, it's like quite a loose cannon grad student. I asked it to calculate the metric on a moduli space. That's a fairly sophisticated bit of mathematics, a bit beyond textbook, but it's something that a grad student in a month could do. And ChatGPT can do it in 12 seconds, but it also does it wrong. So, you know, I don't know. It's exciting though, isn't it? What it does do is helps you contextualize ideas. You know, I think communication, for instance, is not normally a strength of theoretical physicists. Well, this is a tool to do that. It's brilliant. So lots of things can be done with it. I don't think it's going to replace the spark the spark of genius at the next level. I think that's, I hope, going to come from somewhere else. I mean, Geert would disagree, of course.
Okay, if I just may, I think reach down here, there's something to remember this special moment by, and there'll be a photo opportunity later on, but there's a paperweight. I
Oh.
feel like we should have actually got one of
There
those
we are.
chalk dusters actually
I'm-
engraved. But,
I'm touched. Thank you so much.
Anyway, let's show our appreciation for Dan.
Thank you. Thank you very much.
Thank you, David. So yeah, thank you for that introduction. As I say, quite a broad interest, I guess. I mean, I'm going to start actually by just saying, thanks to Dan as well. I really enjoyed your lecture there. Now I'm going to take everybody back to a sort of, I don't know, maybe a mid-2000s average student night out. Okay, so what happens is, Dan has got you all going now, right? You're midway through the night. I'm afraid to say you peaked, okay? Dan's got you all going. He's got you intellectually stimulated. But if we let you go out of this room like that, you're going to be a danger to yourselves and others. So I'm the slow dance that's going to bring you back down to earth and make sure that you're safe to depart. Okay. So what I'm going to talk about today is just a little bit of background. By that I mean personal background. And then touch on research and innovation. It would help, I guess, if I covered the talk title, because that's what people will be expecting. But also, I've had a kind of a strange career pathway. We all have strange career pathways. We're all individual. But given that I've now got this research culture role, I thought it might make sense for me just to talk a little bit about what research is, what research and innovation is, what research culture is, and how we should try our best to look at how we recognize research and innovation activities. And then a little bit around what next. It's funny that we both picked that. I mean, from my perspective, I didn't really want to draw any conclusions because, unfortunately, I recently saw my USS pension statement, and I realised that there's nothing to conclude yet because I've got another 28 years to go. So, for personal background, as I say, I was born in Swansea. I was born in Mount Pleasant Hospital. It is not a mountain. It is subjective how pleasant it is. I then went to Mansleton Primary School. Not long after I was born, they closed Mount Pleasant Hospital. Not long after I finished in Mansleton Primary School, they closed Mansleton Primary School. There's a member of FLT who went to Mansleton Primary School as well, but I'll leave you guys to work out who that is later. I moved to Plymouth. Plymouth didn't close. Not that I'm aware of anyway, but I came back to Swansea. Swansea's weird like that, it brings you back. So I came back when I was 18, studied an M.Chem with a year in industry. I was first generation university in my family, and I had a plan when I came. The plan was this: I was going to teach chemistry to school children. That was my aim, secondary school. But I didn't want to go from classroom to university to classroom, which is why I chose to do a year in industry. Unfortunately, I really enjoyed it. I loved it. I worked with 3M up in Atherstone, in the process of closing at the moment. So, but 3M in Atherstone, it made, you ready for this? Sandpaper. I was a resin chemist in a sandpaper factory, working on the R&D, and I absolutely loved it. And it made me look at the world really, really differently because I realized how much thought, how much energy, how much research, innovation, development was going into making sandpaper. So everything becomes infinitely more exciting when you look at the world like that. So I wasn't going to be a teacher anymore. But the problem is I was doing an M.Chem with a year in industry, which meant that I spent the final year in a research group. And then annoyingly, I really enjoyed that as well. So now I was told, the one thing that I did know is that I didn't want to be a teacher in a secondary school anymore. Teenagers are hard work. But that's the story. Really unfortunately, a tough time across the UK, and we started to see, and there are people in this room, not just Swansea University actually, but other universities, where we started to see the closure of chemistry departments. That was a really, really hard time. And we'll probably touch a little bit on that later. But not everything that closes is closed forever, I will say that. I moved on to materials science and engineering, where I did an engineering doctorate sponsored by BASF and Chorus at the time, aging myself, now what would be Tata Steel. Not closed, okay? Not closing. And neither is this place, and we're not going to let either of those things happen. Okay, so every now and then in this, because I thought about what I was going to do, the strange thing about an inaugural is that you've got the freedom to do what you like, which sounds wonderful when you first start thinking about it. It becomes really challenging when you start seeing the reminders coming out in the all-staff emails, and you're like, oh, I better think about something that we're going to say. So I've decided that actually I'm going to try and make this more about people in the audience and trying to give bits of tips and advice, particularly for those who are still climbing the ladder. So my tip is have a plan but be flexible. I'm not, well, never say never, but I'm not teaching in secondary schools, but I am doing what I consider to be probably the greatest job in the world. So research and innovation started right back in the chemistry department. The idea there within that research group, I was a small part of it, and I think that is a point that I want to make throughout all of this. Yes, it's my professorial inaugural, but you're going to get really bored really quickly if I spend, and also if you all came here and expected me just to you know, have you ever been to a talk where someone's just told you how brilliant they are all the way through it and gone out convinced that they were brilliant? Because I never have. I think this is about the fact that everything that I've ever done has been a team effort, which has had lots of people involved in it. What we were trying to do back in those days was look at the elegance of nature and ultimately lead towards one-pot synthesis of complex sort of biomimicked molecules. So natural products that we see around the place, still an active theme within Swansea, but our aim was to try and do that in as simple a way as possible. Elegant. Okay, I was thinking about this as Dan was talking, and we had a little chat in between. There's something about that sort of unity and elegance that, and also that kind of cost function of everything. When you look at how complex biomolecules are, if you try and make them step by step, you're going to have efficiency issues at every step. So when you add them all together, you end up with a really poor yield. If you can try and do things in what might at first instance look like a slightly less efficient process, but you're cutting down steps, the overall yield becomes bigger. And that's what we were really trying to do. This was the start of a load of things that went, that sort of carried on from there. And this was a really simple piece about just making a catalyst, making a heterogeneous catalyst. So a solid support function made out of an aluminosilicate structure, big porous structure. Porous structures became kind of a feature of life from there onwards for me. But ultimately, the way that you would do these things, it was, again, kind of cool, kind of elegant. For the non-chemists and physicists in the room, yeah, both of you. If you can imagine making papier-mâché, okay, this is basically what we do. We make a solid chain. How do you make a big sort of hollow shape within papier-mâché? You blow up a balloon, you put papier-mâché around it, and then you burst the balloon. That's pretty much what we do with a technique called surfactant templating. We take a load of surfactants, soaps for the for people who speak that sensible language, and we make sort of bubbly structures. We build our catalyst around that, and then we burn out the stuff that's in the middle. That's, again, my interest is making porous things and drying porous things. This went on, I mean, this is probably the least, well, it is the least sophisticated piece of that work, but it came out of an MChem project. There were a few more papers that came later from this in increasing sophistication as we functionalized bits of that catalyst structure. But I did say I was going to keep coming back to the research culture piece. I checked on this recently just to make sure that we were doing good practice in those days. And I checked the acknowledgements, and I'm really pleased to see on there that we did thank Pete Davis, Smiley Pete, to those of you in the know, for his contribution. And this is something that we can do, right? And I can see some awesome people from my past in the audience as well. I'm going to embarrass you now, Stan and Mike. The research technical professionals, retired research technical professionals. Tangential story. Now, last time I saw Stan was in his birthday. I'm not going to put a number on it, okay? It was a big number. And I said to Stan, so Stan was a technician in the chemistry department, and I say Stan and Mike kept everything kind of ticking over for us. And I said to Stan, I said, you lot just seem to be, I don't know what it is about chemists, but since you've retired, you look, well, if anything, younger. So I said, it must be something about chemistry. It must be something about what we're using, which, I don't know, pickles us or something. And in unison, both Stan and Mike said, no, it's retirement. So thanks for that nugget of advice. Anyway, that was my interests. And as I say, these were really, really difficult times. We were in a department that we knew was closing. And resources were incredibly constrained. And I tell you this because this is quite interesting. We didn't really have enough silica to fill up chromatography columns. Again, I'm speaking to the chemists now. Other people are going, what's he on about? But basically, great big tube with a load of packing at the bottom, and then silica layered up through it, enabling us to separate our products. So we were doing that in pipettes, glass pipettes that we were holding together, a little bit of cotton wool in the bottom to pack it, and then we were doing microscale chemistry. Turns out that we were ahead of the curve, because now, so we did that because we were financially constrained. We didn't have enough silica to fill a full column to do this work. What that teaches us is, number one, you can do things at a smaller scale, even though most of my life has been about scaling up. You can do things at a small scale and do interesting science. You can do things when you're resource constrained and do some interesting science. But these were financially driven decisions. Those types of techniques are now being used more commonly because it happens a lot. Things which are sort of financially sensible are environmentally sensible. So I've actually given talks recently for Royal Society of Chemistry on how we did all of this stuff, but it was actually, the motivation then was very different. So my message on this one is that none of this was ever done on our own. Okay, so moving on from there, I wanted to think about, I'd got this real interest in this industrial scale stuff that we'd done at 3M. I'd also got this real interest in university research, and I wanted to do stuff where I could directly see the link to the product. And by luck, really, more than anything, I found a sponsored engineering doctorate project, which was looking at the rapid curing of functional coatings. Well, they weren't that functional back then, actually. This was paint. Sandpaper and then paint. Yep, and I did, many people in the room will know this, I did spend 4 years of my life watching paint dry. I wrote a thesis on watching paint dry. But it's actually fascinating if you're me. And I think the thing about this where it really started to get interesting to me was that I realized that we were producing about 100 million square meters of pre-painted steel in Shotton every year. All came from Port Talbot, so it's Port Talbot steel. Goes up to Shotton. In those days, because I can see him staring at me, Dave Penny was galvanizing it as a member of staff in Chorus before he rejoined us. And then it was getting pre-painted. 100 million square meters a year, keeping the wind and rain out. Crazy. If you look at it from a European perspective, coil-coated, so pre-painted steel that's produced in Europe every year, produce enough area to cover Paris. So the whole of Paris every year could be covered in stuff coming out of these factories. And And again, at this point, still financially motivated, being honest with you, still financially motivated. We wanted to make these processes more efficient, more elegant, use less stuff. Big gas-fired convection ovens. Okay, there's a production line up there for a typical paint line. This would be running at continuously at 120 meters per minute, 120 meters per minute. Strip is 1.2 meters wide. Constantly painting, constantly drying in a dirty, great big gas-fired convection oven. So we effectively, my work was around getting rid of the gas-fired convection oven, moving it to something that can be done faster and enabling us to speed up production and lower the carbon footprint, yes, but I'm being honest with you, it was about costing less at that point. The way that this was going to be done, apologies for those of you that can't read Dutch. This was in a production line in Holland where the gas-fired convection oven was going to be shifted and replaced with near-infrared. So a big part of my work around that time was just exploring how we could cure paint with near-infrared rather than gas. And to do that much, much quicker. So taking something which would normally cure in, say, 45 seconds and taking it down to around 5 so that we could run a line faster and have a shorter oven. Problem is, you've got to do quite a lot of things in that time. So 45 seconds, luxurious amount of time to heat something up, remove all of the solvent that you've mixed in to make the thing flow so that you can actually paint it. And then we have a cross-linker, okay, which had blocked acid groups on it. So effectively, goes up past a certain temperature, 232 degrees Celsius, off pop the blocking groups, and then you get an extra polymerization, which creates a solid film. If you do that before you've got the solvent out, guess what happens? You get solvent trying to bubble through and burst through the film, which is never ideal. So you've only got a limited amount of time to do that, and don't expect people to be able to really see any of the numbers or anything. It's more the principle here that you've effectively got 2 different thermal events. So this is some traces from some differential scanning calorimetry where we heat this material at different rates. Very, very slow, might I add. So the first, the sort of top left there, we've got heating at 10 degrees per minute. And what you can see is a couple of really distinct endothermic events. One of them being solvent evaporation, one of them being this unblocking and cross-linking. And they happen very separately, which is lovely. As you push the speed, you go down to the bottom right, 80 degrees per minute, everything's happening at once. You're just going to end up with a mess. So a large part of what we did in those days was trying to formulate and just understand what's going on so that we could separate out those processes or change them as need be. And then explain that to a bunch of operators in a production line in Holland who have been doing this stuff since before I was born, and trying to convince them that, you know, they were going to have some challenges. That's important. That's a really important thing that we have to do, is how we do that convincing piece and that influencing piece. And I'll be honest with you, I totally messed it up. And they didn't believe a word that I said, anything that I showed them. Who's this kid, I think, was one of the things that came around, until they set fire to their oven, at which point, next visit, things went a little bit smoother, but I had learned a lesson about how we have those discussions. And I think that was quite important for me. Where we went on from, well, went on from there was to really start to understand what's going on within the system so that we can make things a little bit more robust. So many smart physicists in the room that what I'm going to tell you now is that typically when you fire near infrared at stuff, dark colours absorb lots of it, lighter colours reflect quite a few of them, quite a bit of it there. That's effectively the conversation that we had to have on the production line. So if you're changing the colour all of the time, you're going to change the behaviour. But what's quite interesting, of course, is that we're talking about near-infrared, and that's where things get a little bit bizarre in terms of what you can do on a production line. So everybody assumes that titanium dioxide is a really, really good white pigment. They don't assume it is a really, really good white pigment. It's brilliant in the visible region for scattering light. But when you look from sort of 250 nanometers in the UV through to 2,500, pushing well into the near-infrared, you start to see, if you look at the coating system in different ways, that actually you're scattering in the visible region, but you're starting to see artifacts from the substrate below. So, so what you see when you put a coating down on a steel substrate is sort of dotted line at the top there has got a load of really interesting wiggly features, as David, being a spectroscopist, will be pleased to hear me describe it. I know that they're coming from the underlying substrate. So what that means is that light is going through the top coat, down to the substrate, coming back out again. That's really inefficient when you're trying to cure something and get heat into it. It's so a really, really simple idea is if you make the substrate darker, it absorbs more light. Again, blowing the physicists' minds here. And what that translates to is efficiencies on the line and savings in energy and savings in money. But nobody believes it, because the idea of selling a white coating which has got black underneath it seemed like a ridiculous idea. But actually, when you test these things, we could see that visibly it still looks the same. And when I say test, vision is really subjective. So this is taking panels, cutting them up, showing people, getting them to guess which one's got the black primer in it, and also, as I say, proving it spectroscopy and through colour measurement. Why is that important? What does it do? What does any of that mean? Well, when you learn bits like that, you can start to apply it in different areas. And yeah, it was interesting to increase the operating window of a production line and to reduce some of the costs. But the reason that I was really interested in it was that the more that you start to think about how, if you look at that area of spectrum that we were just talking about, it's pretty much where sunlight falls. So if you can get coatings that trick the eye, you can start to do interesting things. And that's kind of what we did at that point. There was, so up in Shotton in North Wales, this building, the Sustainable Building Envelope Centre. For any of you guys that are familiar with the active classroom currently on the Bay campus, you'll have probably heard us talk about steel with holes in it that generates solar thermal heat that we use to improve the efficiency of heating within the building. It's black. Physicists in the room, why is it black? Because black absorbs really, really well. But so does lime green if you're smart about it. And apparently architects prefer lime green to black. So that's the kind of stuff that you can do when you start to understand what these things really, really mean. And then, of course, you start to realize that titanium dioxide is a cool material because you can do other stuff with it as well. So this was probably a point where things got quite interesting for me and my colleagues. There was a lot of buzz around this time about dye-sensitized solar cells. They use titanium dioxide as the semiconductor within a photovoltaic. And it's lovely for us because we can coat it over large areas, and effectively we can create potentially a cheaper photovoltaic but cover a larger area. And that was our aim. It still is our aim. To get to the point where entire roofs, all of that 100 million square meters that we produce a year to keep the wind and rain out, can be doing something else. It can be generating power or generating heat. But to do that, we've got to make the thing. And one of the problems was that there is a sintering step within that process. So we take a titanium dioxide paste. You can print that quite easily with something as simple as screen printing, and I've got colleagues in the room who have done that all over the world. Yeah, I'm looking at Matthew back there, you know, screen printed these things in t-shirt printing presses in Mexico. So we can do that, but you have to dry it, and the quicker you can dry it, the better. So the 30-minute 500-degree heating step with a convection oven, if you were going to do that on industrial scale, a gas-fired convection oven, we found that we could take what we'd learnt about sort of NIRing titanium dioxide as a pigment, do it as a semiconductor, and create a porous network on top of our substrate in, at that point, we were looking at about 12 seconds. So 30 minutes down to 12 seconds, we start to see something that you could conceivably put on a roll-to-roll continuous production line that looks a little bit like making paint. So we patented it, and then we started to build some other stuff. And this was around about the time that the call for innovation and knowledge centres came out from Technology Strategy Board, as they were at the time, now Innovate, and Engineering Physical Sciences Research Council. So Dave Worsley prepared a bid around what we called buildings as power stations, but it was this idea of how we can create innovative functional coatings at scale that do something other than keep the wind and rain out. So I was finishing my NGD at this point, and we patented that. We sort of published a little bit on it, and we started to expand it into other areas. And the idea of all of this was that we could just make the most out of our built environment, generating heat, generating electricity wherever we had a spare surface, storing it, and releasing it at will. And that's the philosophy that really still goes on there today, in good hands. So how did I then, where does that all start to move into the, I'll come to the transdisciplinary stuff in a bit, but around about this period, UK government used to talk about clean growth strategy. And clean growth strategy was okay, but what it did, which irritated me, was it didn't do unity, Dan. It didn't do unity. It pulled everything apart. So it pulled power generation apart from industrial emissions, and it pulled that apart from construction, and it pulled that apart from transport. And that, to me, never made sense. Because if you want to solve a problem, you go back to that original thing I was talking about with a one-pot synthesis. You're going to have efficiency losses all the way along. You're going to have unintended consequences. You're going to have things that kind of butt up against each other and create issues if you try and do them all separately. And that's why I enjoyed that period of time, because what we were looking at is how you could bring all of these things together, because actually those buildings aren't made of fairy dust and dreams. They're made of plastic and concrete and steel and heavy, heavy industry. But they're generating power, and then they're using power efficiently and potentially providing the infrastructure to decarbonise transport. I'm pleased because things have moved on since then, and people have recognised that you need to take this whole systems approach to understand how we do decarbonise. So moving swiftly on brings us up to Sunrise, and I was delighted this morning to join the Tea at Sunrise webinar. Tea being, what is it, Matthew? Remind me. That's the one, Transforming Energy Access. So Carbon Trust Programme, which has taken Sunrise to a new level. But as I say, when I was involved more, we were looking at translating some of the learnings from the research that was going on in our institution and across partner institutions, so across the UK and initially across India, to develop low-cost photovoltaics and improve energy access on a global scale. But to do that, we had to demonstrate. In the UK, we'd been demonstrating with buildings that we produced, but we knew that we needed to do that in the global south in order for people to really understand it and believe in it. But This is where the transdisciplinary piece comes in. Things have to be appropriate for the place in which they're operating and for the communities that they're there to serve. So just doing the really good science and bringing that over and expecting it to work is never going to happen. You have to understand the communities, you have to understand the problems, you have to understand what they're facing, and all of a sudden it's this really irritating for those of us who've come from a pretty quantitative STEM background. I mean, I've done my absolute best to avoid anything that's in any way sentient, because I find it so much easier if I can predict something. If I do that in the lab, it's going to probably do that. And if it's a surprise, then it's, we can work out why. Things that have emotions and ideas and all of these other things, it just complicates the picture. But actually what I began to realize is that always happened anyway. That was happening behind the scenes. All of those driving forces behind my old projects, they were subjective things that were decided somewhere by a human. Why were they investing in that? Even if it's down to a piece of research, that piece of research has gone, hopefully, through a panel of people with opinions and ideas. It's been shaped somewhere by a policy. So actually, what we suddenly realize is that when you haven't got a policy framework, when you haven't got any ideas, you haven't got decades of marketing that tell you that, this is the right thing for this particular product to do, you have to go right away back and do that yourself. And that's why global challenges to me are really interesting, because nobody's got the answers. So you have to work with the communities to understand what they want, what's going to work, what's going to cause them problems. And it's complicated and it's tricky, because it's things like, just as an example, if we wanted to change how people cook in a rural village, you might displace somebody whose job it is to go and get firewood. Their purpose in life is to get up every day to gather firewood. And you're going to tell them that, okay, you're going to feel much healthier, and your respiratory diseases that you don't even realize that you're suffering with are all going to go away, but so is your purpose in life. So actually, it's really complicated. And I think that was quite interesting to me when we started to engage in Sunrise, and it's sort of made me think more about how our research has to embrace all of the other disciplines so that we can position it properly. Okay, so what am I doing at the moment? A few things. I was going to say quite flippantly when David introduced me, there is a shorter version of what I do and what my research interests are. I dry shit. Or I dry shit. It depends how you phrase it. And this got me in a whole world of problems. So effectively, there is a piece of work. I know some of you only came here to find out how long it was going to take until I talked about shit. True story, at an electrochemistry conference, talking about stuff, meet somebody from the Bill and Melinda Gates Foundation in a bar, as you do, and they asked me what I did, and I was quite flippant, and I said, sort of talked about what we did, and I said, really, I dry shit. And he was like, you dry shit? And I said, no, stuff. I was being flippant, And he said, no, but have you ever thought about drying shit? I can categorically tell you all now, at that point in my life, I had never thought about drying shit. Never crossed my mind. But it turned out this was a program officer for the Water, Sanitation and Hygiene program within the Bill and Melinda Gates Foundation. And it turns out that there's some really interesting things you can do if you dry shit. Because fecal sludge is, it's 90% moisture to begin with. If you can remove that moisture, you're usually in a water-constrained country where you've got some of these issues. But if you can remove that moisture, you've got something with a calorific value that's not that far from wood. You can burn it, people do burn it. You can use it as a source of organic material, which also becomes really important because, again, speaking to the chemists in the room, if we don't have oil and gas, and, I would love to see us no longer pull dead dinosaurs out of the ground, but if you do that, then anyone who's an organic chemist will tell you that organic chemistry is the study of what we do with stuff that comes from crude oil. And that's everything, including the paint I talked about earlier. So we'd have a problem. Anyway, that is why I've got that image there. That was a piece of art for researchers' art that came from Larissa Nicholas, who some of you may know. She was a PhD student of mine. She was a master's student of his before that, and went on to be one of our I&E officers before going back into research in Dubai. So we worked together on some of the fecal sludge stuff, and she was working on growing things from that. Okay, so yeah, what am I doing? We've got the Place-Based Impact Accelerator, which is really about helping other people to run projects that can contribute to net zero buildings. I'm working on a couple of small projects on demagnetization to recycle stuff in wind farms, and this link is almost certainly not going to work, but I'm going to try it anyway. Oh, it is going to work. And a whole host of living my life through my PGRs, who are wonderful people. Oh, that hasn't come up, has it? Oh, okay, that's a terrible idea. Hang on. Oh, there we go. A couple of reasons for doing this is because it shows you a few things. Number one is it shows you that I do live my life now, my research life, through my PGRs. It also shows that our website's appalling sometimes. And it also shows you that at the moment we don't name our PGRs. Something we've got to sort out. Because these are people that are really driving these projects forward, and I could take all of the credit, but I'm not going to, because actually the exciting work most of the exciting work that I did was when I was a PGR or a postdoc. Now I shepherd others. Okay, that is what I do. But again, a range of things from looking at steel making through to replacing fossil fuels in paint formulations, and moving on to looking at microplastics that get released when those paint systems weather. Anyway, enough about me because it's getting tedious now. But I think, again, communications and partnerships are really important. That's what drives all of these things forward. It's not one of us, it's about what we do together. So moving on to the career pathways, or my career pathway. It's been odd, it's been a journey, it's been strange. The first thing that I guess I did was I worked in as a postdoc, which was really around scoping before specific was awarded. We'd made some discoveries, and we wanted to figure out how we could, lay the seeds for some more. And then as a technology transfer fellow. During that time, I got with science communication in general. So myself and Richard Johnston secured some funding, which then ended up paying for a bit of me to go off and talk to people. This was amazing. And what did I learn from this period? Well, techno-economics was important in that end of the scale as scientific developments. Making these things viable so that they were interesting and could work was really, really important, and leads to those subjective decisions about funding of what people actually want you to be working on. We had a fun time with lots of engagement, and I did some stuff that I loved, which was talking to people about cool stuff that other people did. I then became a project manager. So a project managed our CDTs when another person in the room became an academic. Important point in this one. Suddenly I'm in professional services. That's weird. I thought we hated each other. I thought that was the plan. I thought there is no divide. We're the same people with the same core mission. We're trying to do the same stuff, which is make good things happen. And I loved that, because otherwise I would have to have a real problem with myself. But it was a chance to develop and mentor and manage others, and that's eye-opening as well, because again, you can live your life through others, which is much more fun. I became a teaching enhanced senior lecturer, teaching enhanced. Ian helped me a lot with that. So again, not only am I supposed to hate all of the professional services, there's supposed to be a divide between research and teaching, right? No, unity. It's all one thing. We've all got one big mission, to create new knowledge and to share that for the benefit of communities. And I really enjoyed that. And also, for those of you who are PDRAs, so I'd done quite a bit before I got my first permanent contract. So I do feel your pain, and I know it's a really, really challenging period in life. Again, chance to enhance knowledge, work on curriculum development, and really reflect on those pieces that make a degree work. Then I became an I&E Enhanced Associate Professor and the Chief Operating Officer of Sunrise. In that period, I think that the really important thing to say is that I loved that pathway. And I think that's an important point to make now. I loved that pathway. It was a brilliant pathway. It was ahead of its time. I can see all the SLT going, oh God, what's he doing? I loved that pathway because what it did was it allowed us to recognize a broader set of activities. Some of the stuff that I did would have looked weird in a research-enhanced career. It really would have looked quite strange. It recognized that wider contribution to the research and innovation community. It recognised things like the work on UKRI panels, on Research Wales Committee. It recognised the things that it did in professional bodies, and that's how I first met David, actually, Professional Standards Board at the RSC. And it recognised the work, and it's a lot of work, and he's run off now, but I talked to Hans about this a lot. It's a lot of work to build and maintain external relationships. And I know this is hard for a lot of I&E people because sometimes what you feel when you're doing that is that, and it's a good thing, you're doing it for the benefit of everybody, because what you're trying to do is create a stronger institution where others can then step into those partnerships and work on them. And I thought we were ahead of the curve with I&E in that we acknowledged that. I became the EPI lead, as David mentioned, which was again an opportunity to step into leading within the university, and an increased personal focus on collegiality and service. And then, as I say, that helped me. I will say that helped me on the journey to an I&E Enhanced Professor. Again, still got that I&E thing, which was again a proud moment. Became the DPVC for Research Culture and the Massai Director, so professorship happened in 2023. This happened on the 1st of April, yes. And now I'm an enhanced, no I'm not, I'm an Education and Research Professor. There's not an echo, that is the title, Education and Research. Sounds a bit odd, doesn't it? They're really getting nervous now, thinking, is he going to give us a good kicking about pathways? Of course I'm not going to give you a good kicking about pathways. And there's a reason that I'm not going to give you a good kicking about pathways. And anyone with a keen eye may have noticed what I've been doing all the way through the presentation with the titles. All the things I've talked about are the criteria that are going to sit within the new pathways. And this is particularly important to me because I know it is there. You're not going to be able to read this, but actually what you will start to see, if I go down to Professor on Education and Research, you'll start to see the things that start to jump out. That's the one, isn't it? Yeah. So around education, I've sneaked all of these words into the presentation, right, by some sort of odd neuro-linguistic programming. And the thing is, I started with a contribution to the generation of knowledge. I talked about the wider research and innovation community, and I've talked a little bit about outcomes, impacts, projects, activities, and then this collegiality, leadership and management piece. This has actually reassured me writing this project because writing this talk, because it forced me to go through and figure out, does it all cross-correlate? And it does. And that's really important to me in the next part of what I do as DPVC Research Culture. Right, this is an in-joke for the chemists, by the way, so don't panic too much. I'm now going to start the second half of my presentation. One of our colleagues actually did that to some students. Okay, so the future for me at least. The reason that I mentioned all of that is that research culture is a really strange word that we use, and that is going to be a big focus now. Yes, I'm going to be living my life through my PGRs, and they're going to keep me entertained and informed because we're going to work on discoveries together, but they're doing so much of the legwork and they need the credit for that. But actually, research culture is going to be all about how we recognize that broad contribution to research. And that doesn't mean that we don't recognize traditional excellence as well. That's really, really important. And we have some traditional excellence in the room, people that you know I would consider personal heroes. Mike, I'm looking at you there. But I think the point of all of this is that when we look at our pathways, when we look at things like COARA, the Coalition for Advancing Research Assessment, the UK Reproducibility Network, and the work that we're doing around that, this is about making sure that anyone who is contributing, that's our professional services staff, those unsung heroes that are enabling us to create an environment where we can do good research and get recognition. It's about recognizing technicians who have helped us to, again, to advance the things that we couldn't do without them. And it's also, I think, about recognizing diverse contributions, both diverse in terms of type of research, but diverse backgrounds that contribute to our research. Because only when we do that can we really get the answers to some of the tough challenges that face us in the world. And I've purposely hidden it-ish down in the bottom right, but this is such an important part of REF. Okay, yeah, there we are, lost them all. REF is a measure, but REF is our opportunity in 2029 to talk about people, culture and environment, and to make sure that we are doing those things. And actually, Swansea's pretty good. I mean, oh, you're still here, that's good. I was going to say, Biagio is the set of shoulders that I'm standing on this as the previous DPVC research culture. And we've got Anna, a research culture manager as well. It put us into a position where we are, and people don't know this and it irritates me, we are co-leads of the UK's national chapter for the Coalition for Advancing for the advancement of research assessment. We are the people which are helping the UK to lead in terms of recognising broader contributions to research. We are a case study institution within the UK Reproducibility Network for the work the ongoing work, before any of you lot get picky, on our open and responsible researcher reward and recognition activities. So this is about the reform that's been done around academic career pathways. It's about understanding that the contributions that people make and the improvements that can make to our culture. And from the Maasai perspective, we've brought Maasai together with research culture in my role because that notion of transdisciplinary research, that challenge-driven sort of stuff, fits in well with a narrative and an understanding of what we mean by open research, which isn't just publishing in open access journals, might I add. Okay, I'm not going to go into a world of acknowledgements because the problem with a role like mine is if I leave anybody out, that's going to be horrific. So all I'm going to say is that you're all brilliant, and actually you're all part of it. So I'm going to acknowledge you all because you've all turned up, so listen to me ramble. And as I also said, I'm not going to conclude because I haven't finished yet. Another 28 years of this. Thank you.
Ian, easy
Some
listening.
stuff. Easy listening.
So before we close though, I'd like to open it up to questions from the floor. So any questions for Ian?
Oh, he would, wouldn't he?
So being very polite, where do you see your fecal sludge work going in the future?
Really interesting, actually. The fecal sludge stuff. I did think about giving the crowd what they really wanted, which was me to talk shit for a bit. I mean, I kind of did that, but I meant literally. It's going in a few different directions. So, as you will well know, one of the things that you can do is turn it into biochar, which is a useful material in lots of ways. But I think there's broader stuff around this. So when we got into fecal sludge, it was about understanding the mechanisms of drying, trying to find more efficient ways of doing it. And there were a few projects which looked at infrastructure. So we took things, so in Durban, we've got a setup where we've taken some transpired solar collectors, some of our PV cells, and we developed a sort of a solar drying system out there. What's really, really fun and what I love doing is joining stuff up. So at the moment, that work sits with Ben Evans, who I'm sure many of you will have known, and hopefully some of you will have seen his Inaugural around us. So he was in the same group of promotions as us. And Ben is now looking at he's actually CFDing shit drying. And he's doing that to, again, partially to help with efficiency there, but to look at toilet designs, because this goes right back to how can we make accessible sanitation in those areas. If we can get on-site processing done efficiently, done passively, not using too much energy, then it does a few things. It means that we actually reduce the bulk as well. So even if we have to transfer that to a treatment site, we're not carting around a load of water. So at the moment, that sits with Ben, who is CFDing supersonic cars and toilets. It's a funny place, this, isn't it? I love it. But yeah, ongoing work as well. I mean, I haven't got anyone specifically on it at the moment, but still got interests in how we can go back to, it's basically a carbon source. What can we use that carbon source for? We've stuck it in electronic materials and all sorts of things. And as you well know, we've grown tomatoes. Lovely.
I think just to note, there's a group in Imperial that made aviation fuel.
Yeah, we know those guys. It's probably unsurprisingly, it's quite a small community.
Yeah, thank you. That was really cool. I really like the way you've used sort of pragmatic problem solving, but actual science to solve sort of real problems and save energy, save materials, things like that. So we're hearing a lot about getting to net zero, and in a similar way, we need to solve lots of other similar type problems in a way, and look at the whole. I'm not sure how well we're doing. Are there any things you've been doing that gives you hope that we will be able to get together and come up with those sorts of use science in a pragmatic way to solve some of the energy problems we're seeing?
Yes, but and there we are. The yes is that I think there's loads of really neat solutions where you get symbiosis from one process to another. Again, looking at certain people who've been teaching me about this for years, Reese and Matthew and the gang. But I think the barriers aren't always technical. And I think that's our biggest thing, and that's why transdisciplinary matters so much to me now. Do you know what I think the biggest advancement's going to be? I hate saying this, given what my background is, but I don't think it's going to be that. I think it's going to be getting our creative writers to convince people that we're not a bunch of nut jobs. I think that's our challenge. I think it's making this mainstream. It's going to sound really weird and cheesy, but it's sort of encouraging people to dream a little bit about the future that they want to live in. And then working back from that, because I think that's one of the problems, and I'm really going to offend most of the people in this room now, But as scientists, engineers, technologists, we think that we're creative, but the creative industries aren't our industries. So when you think about that, and you think about some of the developments that we've seen, where did we dare to imagine them? And I think that that happens perhaps in fiction. You know, it's the old thing, isn't it? Science fiction. Did that enable us to dream of having a device in my pocket that means that I can talk to anyone in the world? Did that then, you know, subconsciously engage the people with the wherewithal to design that thing to make it so? I think that's the piece for me. I think there's a bit around just respecting each other across the community so that we understand that we've all got a role to play, and then taking the cues. So that to me is true, getting into true interdisciplinary, transdisciplinary stuff. Tell you what interdisciplinary is not, is an inorganic chemist working with an organic chemist. I'm not going to reopen the mathematics and physics debate. It's a spectrum for sure. So I think that's the issue. I think loads of cool stuff out there, seen loads of cool stuff, could bore you to tears with it, but none of it's going to work unless people believe in it. And a lot of that's going to be around creating demand. And creating demand is probably not necessarily done by me.
In this difficult time of cost options, how are we going to work together to do good research?
There was always going to be one, wasn't there? I was waiting for that. Yeah, it's really, really difficult. It is. It's a challenge at the moment. I think the most important thing, though, is that we don't lose sight of why we come here. You know, like, I think that's the biggest thing. And I was talking to a colleague earlier about this, and you know, we made a really odd career decision, didn't we, to be here and to do this. So there's something that's motivating us. I don't think that's going to go away. It's just hard, but also, and I look to, you know, I'm going to put this politely, the more senior stroke mature colleagues in the room, we see cycles all the time, and I think that's an important thing for us to remember as well. Is basically my ask is that we don't give up or let go of that hope, because we all have a really, really important job to do across all of those things, wherever we're trying to deeply understand the fundamentals of the world that we live in, because actually that's where the biggest impact will come from, is when we make a step change discovery in some of the stuff that Dan was talking about earlier. If we can understand things better, we can change how we do stuff. Right through to people who are working with communities that are, you know, struggling to understand energy poverty or having health issues. We're all of us motivated to do something that's good and right. So I guess that's my evangelical piece, is please don't ever lose that. And I think that things will sort themselves out. We have to be a little bit frugal for a while. But at the same time, when I go right the way back to that first bit, it's funny what you learn when you're resource constrained. And actually a lot of the communities that we work in are resource constrained, and they're really, really inventive. So sometimes you don't solve all of life's problems by having all the gear and no idea. So I think that's something that we should bear in mind as well. But I'm not taking anything away from the pain. And I think, again, we all just have to come together and enjoy those research moments as well. And write bids. There we are. Write lots of bids. Write bids until you got them coming out of your ears.
One final question. No? I was going to ask them if it's awkward. Oh, yeah. What happened to dye-sensitized cells?
They evolved, you see. Science is a wonderful thing, full of things that evolve into other things. And I think that community is people far more qualified than me in the room to answer on that. You know, I did a little bit of dye-sensitized stuff. I dried stuff. But that it evolved, and I think the work that you see in perovskites, the work that you see in OPV, which always ran parallel to that, is using those skill sets. And also, actually, there's a really important point in there, is that, you know, there's still niche applications, but I think when you're learning something, you can usually apply it somewhere else. And I think that's really important. The NIR work, I mean, that was just fun. We did all sorts with that. From, you know, an unfinished dye-sensitized solar cell is a heterogeneous photocatalyst for water purification. You know, the same process, if you just change the material that you're creating a porous network of, it becomes a fuel cell electrode, it becomes a battery electrode, and we did all of those as well. Even down to sintering of silver inks and copper inks, so that any printed electronic could use those principles. So I think that's just a message as well to those coming up. Don't get disheartened when your field loses popularity, because it's not about a popularity contest, it's about contribution to knowledge. And the contribution to knowledge is the bit that's transferable to other stuff as well.
Thank you, Ian. So before I present Ian with this prestigious award, I'd just like to say how nice it is to see faces from across the university, faces from the past, some people I haven't seen for many years. So it's lovely to see everybody here today. So with that, I'll present Ian with your paperweight. Apparently has got your name on it.
Oh, wow. Javier. Remember Javier, guys? I'm going to get a photo of this. I'm going to send it me with my paperweight, because he's going to think that's redundant, right? Because we all went paperless years ago. Apparently.
It is actually, it's quite nice.
It is actually, it's lovely, yeah.
I'll take it out and show you people.
Yeah.
And it is
24 carat.
quite heavy, quite heavy. Looks expensive, huh?
24 carat perspex.
So, with that, I'd like to close the session and to thank Dan and Ian again for some really lovely lectures. Put your hands together for him.
Cool. Well, that's it.